Okay, so in this video, we will consider a few additional examples of U-substitution. Let's take first an indefinite integral. So we'll integrate quite simply x cubed over x to the 4 plus 2 dx. And as always, the rule of thumb is you look for a function whose derivative is multiplying the expression. And you can always be off by a constant multiple. That's always easy to fix. If you look here, x cubed is multiplying the expression, and our denominator is a quadratic polynomial. If you find the derivative of x to the 4 plus 2, you get 4x cubed. Well, forget the 4, it's x cubed. So this is the perfect setup for a u substitution, replacing x to the 4 plus 2 by u. So let's start replacing. Everything in terms of x must be replaced in terms of u. X to the 4 plus 2 is u. And now to find our dx as a function of du, we differentiate. U is a function of x, so we can take its derivative with respect to x, du over dx, and the derivative of x to the 4 plus 2 by the power rule is 4x cubed. Multiply by dx, and so du is 4x cubed dx. But what's left over? We've replaced the x to the 4 plus 2 by u, so that's done. And now we have to replace the missing piece, which is x cubed dx in terms of u. Well, not quite. To isolate x cubed dx, our missing piece, we have to divide by 4. So 1/4 du will give us x cubed dx. And now we can replace. The second piece, x cubed dx, is simply a quarter du. So times 1/4 du. Well, the quarter is a constant multiple. It can be factored out of the integral. So you have a quarter integral of 1 over u du. Well, the function's derivative is 1 over u is, of course, a ln of u in absolute value. So all we are left with is 1/4, the ln of u in absolute value, plus, of course, the arbitrary constant of integration. And now we're done with the integration. But as always, since we had an integral as a function of x, we must give our final answer back to a function of x. Well, that's quite easy, as u as a function of x is x to the 4 plus 2. One last thing you can do here, as x to the 4 plus 2 is always positive, we can drop the absolute value for regular brackets, as it can never be negative. So the integral of x cubed over x to the 4 plus 2, by using a simple u substitution, is a quarter ln of x to the 4 plus 2 plus the constant of integration. And don't forget, you can always verify your answer, right? You supposedly have found an antiderivative to the integrand, so if you differentiate your answer, you should obtain the original function. I will of course leave that up to you. What if we now take the same problem but turn this into a definite integral? So what if we ask now to evaluate the integral from 0 to 1 of x cubed over x to the 4 plus 2 dx? Well, everything stays the same. We make the same substitution, right? So we're still letting u be x to the 4 plus 2. And based on the previous work, a quarter du is x cubed dx. So we'll just use that right away. So a quarter du was our x cubed dx. So the integrand, not worrying about the bounds, will be the same as before, right? It will be simply 1 over u, 1/4 du. 1 over u times x cubed dx. X cubed dx is a quarter du. So 1 over u times a quarter du. But now we have to find the new bounds of integration, right? This is saying x is equal to 0. This is saying x is equal to 1. This is now saying u equals something else. So we're asking when x is 0, what is u equal to? And we're asking when x is equal to 1, what is u equal to? To find the new bounds of integration, well, this is quite easy, right? U is x to the 4 plus 2 for any x. So if x is 0, this goes away, and now u is simply 2. When x is 0, u is 2. When x is 1, well, u is 1 to the 4, which is 1 plus 2, 3. So, when x is 1, u is 3. So 0 becomes 2. 1 becomes 3. And now that we have the new integrand as a function of u, the new bounds as a function of u, we can leave the old integral behind and never go back to x and finish this off as a function of u. Well, we have the quarter. Constant multiple can be factored out. Integral from 2 to 3, 1 over u du. As we've said before, the integral of 1 over u is the ln of u in absolute value. By the fundamental theorem of calculus, we evaluate the antiderivative at both endpoints, then subtract. 1/4 is a constant multiple, can be left outside. And if it is left outside, then we have simply the ln of 3. We can drop the absolute value as 3 is positive. So ln of 3 minus ln of 2. Once again, 2 is positive. We can drop the absolute value. And that is our final answer. One thing we can do is slight simplification using properties of logarithmic functions. Ln of a minus ln of b is ln of a over b. So ln of 3 minus ln of 2 is just ln of 3 over 2. And that is our final answer. So if you integrate from 0 to 1, x cubed over x to the 4 plus 2 with respect to x, the answer is 1/4 ln of 3 over 2, or if you prefer 1.5. And that's it. Let me now just give you one more example of something that will look a lot like this, but with just a slight tweak to show you that sometimes the U-substitution may be hiding, and you have to do a bit of work to pull it out. So, just to remind you, the example we just did was x cubed over x to the 4 plus 2 dx. And now what if I just change the x cubed on top? I will leave everything else the same. So over x to the 4 plus 2, but I will change the x cubed for an x to the 7. Same question, of course, find this integral. And you might think on the surface, well, we can't do a u-sub. The only expression that multiplies the expression, the integrand, is x to the 7, but the derivative of x to the 4 plus 2 is 4x cubed. X cubed, not x to the 7. So you might think, well, it's not going to work. Well, the idea is there is an x cubed here. If we pull it out, this is x to the 4 times x cubed. So we can tweak the integrand a little bit to now make the U-substitution slightly more apparent. The derivative of x to the 4 plus 2 is 4x cubed. Up to 4, it's just x cubed. And x cubed multiplies the expression, so perhaps a U-sub will work here. Well, let's see. So we're letting u be x to the 4 plus 2 as before. Let's start replacing. X to the 4 plus 2, that is just u. As before, to get our dx as a function of u, we must differentiate. So u is a function of x, differentiate u with respect to x, du over dx, but the derivative of course is simply 4x cubed. Multiply by dx, and so du is 4x cubed dx. But as we have here is not 4x cubed dx, but simply x cubed dx, we must divide both sides by 4. And that gives us that a quarter du is x cubed dx. So our x cubed dx here is a quarter du. So times x cubed dx times a quarter du. The difference from before is that we have an x to the 4 left over. And if you think of it, everything in terms of x must be changed to something in terms of u. Well, what is x to the 4 in terms of u? Well, if u is x to the 4 plus 2, we can isolate x to the 4 simply by subtracting 2 on both sides. And so u minus 2 will be x to the 4. And now we can replace x to the 4 by u minus 2. And now we're good to go. From the original integral, everything in terms of x has been replaced by something in terms of u, and now we can integrate. Scalar multiple, factor it outside the integral. And now we are asking, how do we integrate u minus 2 over u? Well, the answer is, the only way to integrate this is to divide through by u. So we'll have a quarter integral of u over u is 1 minus 2 over u equals a quarter multiplies the whole thing. The integral of 1 with respect to u is u. The derivative of u is 1, so this is u, minus 2, and now we integrate 1 over u. Well, the integral of 1 over u du is, of course, ln of u in absolute value. Plus, of course, the arbitrary constant of integration. Well, we could multiply by a quarter to simplify the 2 here and give us a half and a quarter if we wanted to. So we get a quarter u, or simply u over 4, minus 1/2 ln of u in absolute value, plus c. And now the final step. The original integral was with respect to x, so we must give our final answer with respect to x. But, oh sorry, yeah that's right. So u is x to the 4 plus 2, so we now simply replace every u in our expression back in terms of x being x to the 4 plus 2. So we get x to the 4 plus 2 over 4 minus 1/2 ln of, and again because x to the 4 plus 2 is always positive, we can drop the absolute value. And there you have it. The answer to our original integral. Now there is one last comment that I want to make here. It's a subtle one, but it's worth mentioning. Look what we have here. X to the 4 plus 2 over 4. What if we divide across here? And write this as x to the 4 over 4 plus, well 2 over 4 is 1/2, minus 1/2 the ln of x to the 4 plus 2 plus c. And we can simplify this if we just think of, what is c? Well, c is an arbitrary constant. But if you think of it, if you add to c, which is an arbitrary constant, 1/2, the result is also an arbitrary constant. So the 1/2 here can be swallowed by the arbitrary constant c. And here you can, of course, abuse the notation. You could use a different letter for the arbitrary constant, but we'll still call it c. So our antiderivative is x to the 4 over 4 minus 1/2 ln of x to the 4 plus 2 plus, as I've just said, as c is an arbitrary constant, c plus 1/2 is also just an arbitrary constant. And this makes our final answer look a little simpler. So, the lesson here in the end is every time you have some constant or constant terms floating around, you can always just dump them in the arbitrary constant. As a result of an arbitrary constant plus any other constant is still an arbitrary constant. And that's it.